Just over a year ago, the Frontier supercomputer at Oak Ridge Leadership Computing Facility became the first system to cross the exascale barrier on the top 500 list, achieving more than 1 quintillion floating point operations per second. The exascale era is still coming to fruition as the Department of Energy's Aurora and El Capitan systems near completion, and researchers continue to develop software and compilers that can efficiently harness thousands of nodes that include CPUs and GPUs. But entering the exascale era leads to the inevitable question of what's next. Just as generative AI is showing capabilities that could reshape science and society, computing is facing a crossroads, the end of Moore's Law. Computing and its applications will need faster, more powerful processors, but the machines that do the work will change, altering software and programming too. I'm your host, Sarah Webb, and this is Science in Parallel, a podcast about people and projects in computational science. In this episode, we'll examine one part of this puzzle: emerging hardware that could have a place in future systems. We'll discuss quantum devices, neuromorphic chips, and molecular storage and processing. I'll be sharing parts of my conversations with 3 separate guests: Luis Sezzi, Bert DeYoung, and Katie Schumann. They'll share their perspectives on individual technologies and where they might fit in the high-performance computing ecosystem. What are their strengths? What are the challenges? And how will we know when new processors are ready for prime time? We'll set the stage with Luis Sezzi, who wears dual hats as both computer science professor at the University of Washington and CEO at the AI startup OctoML. He describes himself as a computer systems architect, a role he explained to me.
Computer architecture is not just about making a better chip. It's really, I think from a whole systems perspective, is how do you co-design software and hardware? How do you think about future applications and enable them? And how do you think about thermal aspects? Is it going to get too hot? How are you going to cool it? And all of these things.
I asked Luis to describe our current situation in high-performance computing.
Yeah, I mean, we've enjoyed an incredible run in the progress of basic CMOS electronics. We have exascale systems today. And not only that, it just seems common, right, to have petascale computing devices. And I think interestingly, we have really exciting applications to drive high performance computing systems, not just in very specialized settings in science, in scientific development, in R&D, but also in applications like AI. And we've seen this transformation just in the last couple of months in people using this massive scale language models like ChatGPT and GPT-4 that does amazing things. And those are just about the most compute intensive applications that capture people's imaginations in the history of computing. And it's all super exciting because now we have exciting applications and we develop methodologies to design very complex systems that are highly heterogeneous. Today you not only have, CPUs, but also you have specialized compute units in the form of GPUs and specialized AI accelerators in accelerators for cryptography compression. And so we design very complex systems. And that's great. That's going to take us a bit further in building better and better computers. But I think everyone probably heard multiple times that we are nearing the end of scaling of CMOS. Some people call that the end of Moore's Law, but people have been predicting the end of Moore's Law for a while. It's unavoidable that technology is getting close to its limit because it cannot maturize beyond a certain point. Emerging technology is just unavoidable if you're going to continue to build better and better computers.
Bert DeYoung of Lawrence Berkeley National Laboratory made a similar point in our conversation about quantum computing.
One of the things that I realized about 8 years ago is that classical computers cannot scale forever. It's just, we cannot make them smaller, we cannot make them faster. There's too much energy that you have to put into that. So I started to look more at what are other simulation computational tools that we could use. That's where AI and quantum computers came around. And it's like, quantum computers has a lot of opportunities. They have the opportunity to do simulations that are of an exponential complexity, which means they can do a lot of computation much quicker than they can do on a classical computer.
Over the last several years, quantum computing has become a key part of Bert's research.
I do a lot of virtual experiments on computers. So I do chemistry, materials type of experiments that you would do in a lab. I just do them on a computer. And so my interest really is trying to solve important scientific problems relevant to society. Can we find better batteries, a better way to capture sunlight and convert that to energy, capture greenhouse gases, and all of those kind of big scientific challenges.
Quantum computers are exciting because subatomic particles can exist in multiple states at the same time until they're observed, a property known as superposition. Those same particles can also experience entanglement when the behavior of one particle is connected to that of others distant from it. For computing, that means that qubits, the basic units of a quantum system, are not tied to simple ones and zeros.
The challenge with quantum computers, which we realized when I started to work on that, is one, they're noisy, and two, we don't really know how well we can run calculations, simulations on these quantum computers. So that's where I got really interested in trying to find better ways to run simulations on quantum computers, understand where the challenges are, and actually develop strategies and approaches and algorithms and software to make quantum simulation or simulations of chemistry models to actually get chemistry simulations run on quantum computers.
In addition to his own research, Bert is deputy director of the Quantum Systems Accelerator, one of 5 centers funded by the Department of Energy as part of the National Quantum Initiative. QSA is led by Berkeley Lab and includes 15 institutions across the national labs and academia.
What we're really focusing on is scaling up and building more accurate quantum computers in 3 different types: superconducting qubits, trapped ions, and cold atoms.
I'm going to pause briefly and include background information from a version of my interview with Bert that appears in Oscar Discovery. There's a link to that in our show notes. Superconducting qubits are trips constructed with Josephson junctions. Those structures weakly link superconductors, and current flow between them can produce superposition and entanglement. Trapped ion and cold atom qubits are both trap-based approaches. Trapped ion qubits are held in place by an electric field. Cold atom qubits are trapped by tweezers made of light. Lasers coax entanglement and rotate qubits between 0 and 1.
Why are we doing all 3? Let's say we learn something in trapped ions, it's something that we potentially could apply to a quantum computer built of superconducting qubits. So we're really trying to not just build architectures, the better qubits, so to speak, but also trying to figure out how we can scale them up to a large number of qubits. To give you a couple of examples, we've been there for about 2.5 years. We actually have a cold atom system that is of the scale of 256 qubits. We've been able to do real material science simulations at that scale. It's a very different technology and a different approach to quantum simulation compared to trapped ions and superconducting qubits, where with the trapped ions, we just are in the process now of building the first trap that can hold about 200 ions. So that gets to the same scale as what I just mentioned for the cold atoms. If you look at superconducting qubits, we're now in the order of 25 qubits that we can actually do. And it's not just building more, but also trying to find better ways to control the qubits while you have them. You need to operate on them. So, how do you do that with large numbers of qubits? That's a completely different problem. So, we're working on control software, control hardware to be able to run these kinds of qubits. Eventually, we also need to be able to build these in larger systems because we cannot just grow one trap or one system continuously. So we have to start thinking about what do we do next? If we have 1,000, 10,000, how do we actually group them, communicate between them, operate on them? There is lots of challenge. And then that's more on the hardware side. We're also doing a lot of work on the algorithms and software side because eventually, even if we build these quantum computers at this scale, we want to actually solve real scientific problems. Well, there's lots of questions one can ask. How do you know that you get actually a quantum advantage with a quantum computer? So we have been working on developing protocols to actually quantify if you're getting a quantum advantage with a quantum computer.
Work at the Quantum Systems Accelerator has demonstrated a theoretical advantage on a trapped ion system with 15 to 16 qubits, Bert says.
We do a lot of research around how we can run real science on there. So we have some research programs focused again on the chemistry materials, but also on nuclear physics and high energy physics, trying to understand how we can actually use these quantum computers within the quantum system accelerator to do real science.
Neuromorphic computing offers a completely different approach and other strengths, including the potential to use far less energy, up to thousands of times less power than today's CPUs and GPUs. I talked with Katie Schumann, an assistant professor of computer science at the University of Tennessee in Knoxville, about that.
You might be able to tell from the name that neuromorphic means brain-shaped computing. And so in the field of neuromorphic computing, we're looking to rebuild computing from the ground up, starting at the materials and devices all the way up to the way that I think about it from a computer science perspective.
Katie started working on neuromorphic computing and machine learning as a graduate student and for 6 years at Oak Ridge National Laboratory before taking her new job last year.
The algorithms and applications, rethink every aspect of the compute stack and look at all of it from a more brain-inspired perspective. So we're talking about looking at new materials that can more accurately replicate what's going on in biological neural systems, all the way up to what I'm working on, which is figuring out what the algorithms are that we can leverage these properties of brain-inspired computing to do things like machine learning, but also computing applications more broadly in a new way. My personal research is really diverse because I interact with people who are doing hardware development and coming up with new ways to build computers, but I also interact with neuroscientists to take inspiration from the brain into how we're developing the way we're doing computing. Then I also work with people who want to use neuromorphic computers to do something interesting. So my research is all about coming up with the new approaches to do computing, but also figuring out how to design the future hardware to meet the computing needs that we have, maybe for an edge computing application. How do we actually make them do something useful? And are they better than other computing applications or computing systems for those applications? Those are the questions we're trying to answer.
Like neurons, brain-inspired hardware typically spikes to send a signal after it reaches a threshold level.
One of the big advantages to neuromorphic and brain-inspired hardware more broadly is the energy efficiency aspect of it. We're really targeting orders of magnitude lower power than conventional computing systems. And so with that particular property in mind, there's a lot of opportunity to put neuromorphic at the edge for edge applications. Everything from your smartwatch to your smartphone to, conventional things that people are interacting with on a regular basis, your smart speaker at your house, things like that, towards, smart sensors that are deployed out in the world as we do increasingly integrated and smart cities and transportation. We really are going to need these very low power computing operations because we are increasingly devoting more and more power to computing. One of my favorite projects that we're working on right now is a collaboration with researchers at Oak Ridge National Lab looking at applying neuromorphic computing to an edge computing application in the nuclear radiation detection space. And this is an application where they want a very, very low power implementation that could operate at the edge in the field indefinitely on like a small solar panel. And so the question was, for this particular application, can we come up with the right machine learning approach that will map to neuromorphic hardware, that will meet the power requirements for that edge application, and will get as good of an accuracy as other techniques all at the same time. And so having all of that constrained space and working directly with the domain experts in nuclear engineering and dealing with both simulated data and real world data, it's really exciting to try to figure out how to make all of these pieces come together to build a neuromorphic computer that can actually operate on a real world application.
Katie is also working with transportation researchers who are exploring neuromorphic computing for self-driving cars and to optimize fuel flow within engines.
We're also working with people in the high energy physics community where we're looking to apply neuromorphic computing to monitoring data that's being collected in real time at their large scale detectors. My meeting schedule on any given day, I'm pivoting between a discussion about radiation detection to internal combustion engines to neutrinos, high energy physics, just in applying neuromorphic computing.
Katie also works with researchers who build neuromorphic hardware and want to apply it to relevant problems. For example, she's working with a large group of researchers at institutions including Sandia National Laboratories, the University of Texas at Austin, and New York University on emerging device types with magnetic tunneling junctions and tunnel diodes. They're potentially interesting for neuromorphic computing, but they also operate in an inherently random way, which could be useful for probabilistic computing. That's another strategy for addressing problems that are difficult for classical computers.
Think about using these devices as like flipping a biased coin so that you're more heavily weighted to get heads than a 50-50 shot. So that project is actually called Coin Flips because we frame everything in terms of flipping these biased coins, which is how these devices function. And so with that project, we're working with material scientists and physicists and electrical engineers who are working at the materials and the devices level to build these. And then I work at the architecture and algorithms level as we're trying to come up with the circuits and the algorithms that can actually benefit from using these devices at the low level. And again, then we're interacting with the application users who would ultimately use these. And so from that perspective, it's very much like we're starting with the hardware and then what can we do with this really cool hardware implementation, rather than the opposite side where we're starting with the application, the nuclear engineering, and saying, how do we make the hardware that's going to do that? And with these two different sets of projects, the hope is that we can bridge the gap between the two of them and actually say, oh, well, maybe that nuclear engineering project will work with this particular set of devices. I also work with people who are doing quantum materials-based neuromorphic systems and biomimetic material-based neuromorphic systems and memristive neuromorphics, all these weird devices that I, as a computer scientist, only sort of know what's going on, but enough to where we can try to figure out how to use them effectively.
Luis Sezzi, who we heard from at the top of this episode, spends a significant portion of his time working on molecular data storage and computing, yet another emerging technology.
We've been using DNA, but also been looking at proteins too. These molecules can do amazing things, right? So they can store information in a very dense way, and you can also manipulate information in a very parallel and energy efficient way. It's not particularly fast in terms of latency, but it's extremely parallel.
There is an incredible amount of biological data stored in DNA.
So nature evolved DNA to store that maps to genes, right? So DNA contains blueprints to build proteins, and proteins do all sorts of amazing things in living organisms, right? So, but DNA is a fairly general data storage molecule. There's 4 bases, A, C, T, G. If you can develop mechanisms to map digital data strings of ones and zeros into strings of ACTGs, and then manufacture the DNA molecule, physically make the molecule that encodes that information. And you can store them away. And that's when things get interesting. DNA is extremely dense. Like each base is on the order of a fraction of a nanometer, like 0.34 nanometers. Like you're talking about densities that are thousands and thousands of times denser than the limits of what we could get even with 3D flash storage, for example. So denser than anything that we have in mainstream digital data storage today. And that's the process of writing. And when you read it, you run it through a DNA sequencer, the same exact sequencer using genomics. You can read those DNA molecules, but they happen to be synthetic DNA, not natural DNA. They don't encode genes. They encode those strings of nucleotides, right, that you mapped in the first place. And you can run through a sequencer, get long sequences of ACTGs back, and you can decode that back to the digital information. And, this is just amazing. We've been doing this idea, but it has been around pretty much since the structure of DNA was discovered. People say, this looks general. But it took a while for the technology to write and read DNA to mature enough for this to start to be viable. It means that DNA data storage had several ways, kind of like AI had waves of, here's the idea, and then it comes down, here's an idea again as the technology progresses. And DNA data storage started becoming more and more interesting and viable in the past decade as our ability to write and read DNA improved very, very fast. In some cases, faster than the progress in CMOS electronics that we just talked about. And so the process works. So our lab has been doing quite a bit of work in this, but there's several other, significant contributors around the world. There is an alliance today called the DNA Data Storage Alliance that show that this is this is becoming closer and closer to reality.
The DNA Data Storage Alliance was founded in 2020 by Illumina, Microsoft, Twist Bioscience, and Western Digital. Check out the link in our show notes. A limit for molecular systems is that the process of writing and reading DNA molecules remains slow compared with the speed that today's computers can manage electronic memory. Luis notes that it's improving rapidly, but remains at least 10 times slower than today's electronics. At the high end, researchers have stored and retrieved several gigabytes of data using molecular methods. But molecules offer some advantages for certain types of computational problems. Luis talked about how his group has harnessed molecules' ability to bind to one another as a strategy for doing similarity searches, the heart of many AI algorithms. For example, in searching for an image of a bird, a computer isn't looking for an exact match to an ostrich or a hummingbird.
You don't map it by just say birds go with bluebird, redbirds, different species, and all they look like birds. And, so that doing that similarity search in regular computers today is pretty computationally intensive. You have to compute distance in this high dimensional space. We demonstrate the ability to do that indirectly in molecular form.
That's because they realized that a similarity search algorithm could be matched to molecules taking advantage of characteristics such as shape, charge, and other features that allow molecules to bind to each other.
So we developed algorithms that maps feature vectors, descriptors of images into DNA sequences, such that if the vectors that correspond to images are similar enough in their high dimensional space, the corresponding molecules are more likely to bind to each other. So we built essentially this pool, which is a database of a bunch of images encoded in this form, and we put a magnetic particle with a DNA attached to it that corresponds to the image that you want to search. The reason this is interesting is that here's an algorithm that is very, very data intensive. Like when people do this today in regular computers, you do this over 2 years and 2 years of images. It takes quite a bit of compute. But now in molecular form, it just happens in a very parallel way, in very energy efficient ways. That's one clear example of molecular computing that now putting my computer architecture hat looks very interesting because it's not general. Like we're not saying multiply a matrix or, evaluate this expression. You're talking about execute this search, this search step. Very, very specialized, but it's very efficient to do in molecular form.
The potential for all these technologies is tantalizing, but as hardware is improving and changing, that affects software. At the same time, software developments influence hardware. As I was talking with Katie, I was trying to find an analogy to express that idea.
I'm not sure if this analogy is appropriate, but it's almost like you're having to think about the highway system and the cars that go on it all at the same time.
Absolutely, yes. This is the most challenging and most exciting part of this field is that we're building software for computers that don't exist yet, and we're building computers for software that doesn't exist yet. And everybody's just out there working on it at the same time. And occasionally we're talking to each other. That's something we're trying to do in the neuromorphic community is really do this collaboration between the two communities. So we're doing a co-design process. But that's not happening across the board for all of these emerging processors. But it's increasingly going to happen, where you have to be having these discussions so that we're not just building them independently, and then we end up at the end with a car that really doesn't map to the highway that we built, for example, or vice versa. Neuromorphic computing hardware is still very much in its research and development phase. So large-scale neuromorphic chips exist, but really only for the research community, and they're still very much under development. And so it's a challenge because the hardware is constantly evolving, and we're trying to, I'm the programmer trying to be like, what does it look like today, the hardware? What's changed? So that's challenging, but at the same time, it's an opportunity for us to say, okay, I understand the hardware is changing. Could we change it this way so that it is better for my application? I always like to frame my challenges as opportunities to remind myself this is really hard, but it's also an opportunity to do something really interesting. The other major challenge is that we're still actively developing the algorithms for these systems. So nothing is set in stone. All of the algorithms that we've developed over the course of machine learning and all of the advances that we've seen, some of those translate into neuromorphic computing, but not all of them. And so we have to make adaptations, and we have to shift and change the way we're actually applying machine learning algorithms to our data for this hardware. am looking to neuroscience for inspiration on how to do that. Again, that's a huge challenge that I think that is the big challenge that I work on, is how to actually make those algorithms do something useful for us. But it's also an opportunity to pull in all of that inspiration and potentially innovate on what we can do with our machine learning algorithms, particularly on these sorts of applications where we have a resource-constrained environment.
Similar challenges exist in quantum computing. Bert and I discussed the problem of quantum software and translating science into a programming language.
It's not a trivial thing to do. There is no programming languages that allow us to just take a problem and then say, here, write it for a quantum computer, compile it, and it runs on a quantum computer. That didn't exist. So I started to really work on how can we build compilers? How can we build programming languages so we can take a scientific problem, translate it on a quantum computer?
And then there's addressing noise from the science that underlies these experimental processors. Bert also talked about how this plays out in quantum computing.
We're doing effectively physics experiments when it comes to all of these quantum technologies. Well, physics experiments don't happen in isolation. Nothing around us lives in isolation. We always have an environment that perturbs the things. So that's no different for these quantum systems. They're just a lot more sensitive to it. So, in case people don't realize this, but classical computers, the chips have gotten so small that these chips make errors. So, what do? We actually do error correction. So, we run 3, 4, 5 of the same experiments at the same time and just do a majority vote to decide what the right answer should be. Well, doing that kind of an approach on a quantum computer is a lot harder. So you could do full error correction, but we know that if we want to do full error correction, knowing how much noise these quantum computers have right now, that we would need tens of thousands or hundreds of thousands, potentially millions of qubits to even have maybe a couple of hundred really good working qubits. So we need a lot of other qubits to make sure that we can correct the errors that we see. So the root of it is, as I said, it's physics. We try to engineer as much as we can the noise away. So we learn what the noise source is and find a solution for it. Early superconducting qubits were found to be very sensitive to electromagnetic fields, for example. You came by with your phone, you would create some problems. So they put copper shielding around it to minimize those effects. But even the smallest effect at these superconducting low temperatures can perturb the system. We're never getting a perfect quantum computer. We don't even have a perfect classical computer.
So Bert has focused on solving the error problem.
So what we're trying to learn is how we can control these errors, how we can mitigate these errors, both on the hardware, software, and algorithm side. How can we correct these errors? How can we build algorithms that are more efficient so that we don't have to do as many operations that will lead us to get a more reliable result? We take a science problem and try it on a quantum computer, see where it breaks down, learn from it, develop new ways to get more reliable results out of a quantum computer, and then try that. If it still doesn't work, we add another layer of error mitigation till we get the reliable answer that we can get. That's just us effectively learning how a quantum computer works, where its flaws are, and finding ways to do it better.
Luis Sezzi and I also talked about noise and what that means for molecular storage and computing.
It risky sounds a little overly philosophical. It may seem like it's a problem, but I think it's just inherent. That's how you build robust systems. And it's hard to argue something more robust than what nature has done. Sure, we still have, single points of failure in organisms, but by and large, they're very, very resilient and robust, especially at the population scale. The way we deal with that is, first I want to remind, the audience here that electronics in general is noisy, right? So the reason that we didn't build more in analog computers is because analog computers are noisy. So we go and overlay a digital abstraction on top of it to deal with noise. So that's like the very, very basic level. And then on top of a digital system, they can still be noisy. You build error correcting algorithms. You essentially give an abstraction of very robust writing and reading information in whatever medium you have. So that's whole fields in coding theory and how you code information in a reliable way. But then even on top of that, you can build algorithms that are inherently, by the way they constructed, robust to imperfections, right? So we just talked about similarity search. I mean, the whole point there, you want to find something that's similar. and also there's exactly, a perfect match. And then a lot of modern machine learning algorithms work when you train them. It's all an approximation. It's all building, essentially interpolating functions, building functions that can make predictions out of a large collection of data that's deemed noisy to begin with.
In molecular storage and computing, Luis emphasizes that large amounts of data aren't encoded within single molecules.
So what we do is we chop this up into small little chunks. Think of it as each chunk is on the order of, say, 100 bits or so. And each chunk itself has a neurocorrecting mechanism that we encode it in a way that uses more than 100 bits. But there's several mappings of different bits to the original information. So even if you have some bits that are off, you can still reconstruct it. So there's error correcting code within each one of the chunks. But then across chunks, we add extra chunks such that if any chunk is missing, you can still recover the whole information. So it's both within and across. You don't have a single copy of every given item, right? We're going to have quite a few, think of it on the order of tens or hundreds of physical copies of the same original molecule. Each one of them might be slightly different, but they originally map to the same intended one. So now we have three forms of redundancy within this chunk, across chunk, and then physical redundancy. And with all of that, we demonstrated by really stretching to the limit the ability to recover information with all sorts of things, adding air, removing molecules entirely, and diluting it to an extreme degree. And we've been demonstrating like very, very strong robustness in writing and reading information.
An important challenge in this work is figuring out software, not just for quantum systems, as Bert mentioned, but developing compilers and frameworks so that researchers outside these specialized areas can use new hardware. Katie emphasized this issue in neuromorphic computing, which is a field of just a couple thousand researchers. Many of them are hardware developers or people interested in applications rather than software developers.
What we are missing right now, more than anything from my perspective, is the software. We really need software frameworks in place. We need things like compilers. We need software abstractions to be defined that just don't exist right now in the field. And that's partially a consequence of the makeup of the community, because we have a lot of people who are working on hardware. And then we have some people like me who are more focused on things like machine learning algorithms. We have people who are interested in applications, but what we don't have a lot of, in fact, hardly any of, are people who know how to build system software, who know how to build things like compilers, who know how to build programming languages, who know how to define these abstractions. Even though I'm a computer scientist, that's not my background. So I'm not equipped to do that effectively for a new emerging hardware platform. In neuromorphic, we have the hardware. It exists. People are building it all the time. We have these research chips that you can have access to. What we don't have are the software tools in place that make it easy for people to come in and start using that hardware on their new applications quickly. We need the ability to build out these software tools so that anybody can sit down and start using a neuromorphic computing system, and not just people who are experts in the field.
It's incredibly difficult to put a timeline on when and how quantum, molecular, and neuromorphic systems could enter the mainstream computing landscape, but I asked about innovations that could signal that they're ready for broader use. Here's Luis on what that could look like for molecular storage.
I know folks have been using this to store very precious information you can think of, from things like cryptocurrencies that you really want to store completely off the grid, let's say, to things that are nation state information that's secret, or, family information that's very precious. I call this boutique use cases, and that's viable today. But the US government has been very active in investing in molecular data storage technologies, and industry has been very active too.
But he thinks a jump to nearly terabyte level storage would be the point where molecular technologies will become much more interesting.
My academic speculation here, I think we're going to see something really interesting in within the 5 to 10 year range, where we're going to see like pretty exciting archival storage applications there. We're going to start to see applications like data intensive compute tasks like search appearing and being interesting. Can you imagine large repositories of media information stored in DNA and searching for it for various purposes? I think that's probably within the 1 to 2 decades away. We tend to overestimate what we can do in the short term and underestimate what we can do in the long term.
Bert highlighted scientific milestones that could signal that quantum systems are large enough and robust enough to make their mark.
If the scientific community, if we can use a quantum computer to discover a new solar cell material that is 10 times better, That would be a metric. For us chemists, we have set for a long time a benchmark around what's called the FOMOCO system, where we're actually trying to find a natural way to convert nitrogen to ammonia, which is a very important fertilizer problem, which takes like about 1% of worldwide energy these days. And we're trying to build a natural alternative to that. If we can actually use that to build an alternative, that would be a win. But are we there yet? That requires 100 to 200 very good qubits, and we're not there yet.
I asked each of them to talk about what future supercomputers might look like. Would emerging processors be integrated into systems that also have GPUs and CPUs? Or would we see smaller systems focused on specific applications? And the key take home message here is heterogeneity. And here's what Katie had to say about that.
I suspect we're always going to have the very large scale systems. But right now, for the most part, when you look at a large scale system like Frontier at Oak Ridge, all of your nodes in Frontier are the same. They have heterogeneous within the node, so there's CPUs and GPUs, but every node's the same. I suspect that in the future, our nodes are going to be heterogeneous across the compute system, where not every node's going to have a neuromorphic system, not every node's going to have a quantum system, but some of them are. You're just going to have more heterogeneity, not just within the node, but across nodes. And so I think these systems are still going to be large because there are certain applications that map well to those types of systems, but I think that they're going to be increasingly heterogeneous in that it's not just going to be every node is identical, but you're going to have a lot of specialization across one machine. Now, how we program that and how we actually, that's a big challenge that the computer science community is going to have to grapple with. But I think that's the direction that we'll end up going, is that, yeah, maybe you're not going to have a quantum computer in every node, but maybe you've got a couple in your center that are integrated in as part of your system, and you want to be able to use those effectively as you do everything else.
Luis agrees and points out the relationship to the question of where one computer ends and another begins.
I think it's going to be highly heterogeneous. It already is today. So it's heterogeneous with a given specific device technology. Now we're going to have multiple device technologies. And we should also say that it's not just quantum neuromorphic. So it's also, 3-5 materials are coming back. People are talking about cryogenic computing. There's all sorts of different, say, lower level device technologies here that's going to be part of the mix. That's just unavoidable. It's already the case. It's going to continue to be the case. I think that depending on the type of problem, this might be actually multiple, let's say, boxes, each one with their own specific technology. They will primarily combine them later. Or I can also imagine this in a single device. I guess I'm trying to get at here probably is that, what is a computer anyway these days? Like when you run a task, if you go and run a piece of computing, even if it's just like a highly specialized HPC-like application. Okay, so you do the large model computation in a certain box somewhere, probably in a national lab. You get that output, you process it in a different way, now using a different computer, and then you go and render it in a different image, and then, you have what is a computer there? Are you calling the computer just what did the majority of the computation or everything in between, right? So it's already highly distributed anyways, even in things that seem like we're just using one computer, you're not. You're probably using, 10 or 100 different computers in between when you give the input and you get the output back. And we're going to continue seeing that, so, but to an extreme degree. And given that some of these more exotic technologies that we're talking about requires very specialized conditions, like a quantum computer running in these dilution fridges. So in molecular computers or molecular data storage systems are going to have fluidics moving around. I think it's unlikely we're going to have this in our pockets or even in our offices. We're going to have this in a specialized data center that can provide those conditions. And then it's going to be a matter of building a system that's an outer loop that puts everything together.
Burt speculates that novel processors could influence today's hardware in ways that are hard to anticipate.
When we went to the moon, what we had to do is develop enormous amounts of technologies, including actually chips that we use in our computers, that resulted from the vision of going to the moon. I see the vision of quantum also having that same role. We learn a lot about the role of quantum in physics and in building chips. So there might be a future that things we have learned show up in classical computers. So we might, because of the work that we're doing in quantum, develop revolutionary new technologies that could be used in classical computing. We're using fast internet right now to communicate between different classical computers. If we figure out how to do quantum networking a lot more efficiently, maybe a classical computer will be having a quantum network in the future. So there is a lot of technologies and advances that are being made that I see potentially ending up in the world of classical computing. So it might not be just that we have a classical computer and a quantum computer. We might get into a situation where the classical computer is starting to look a lot more like a quantum computer because we're starting to integrate components that we have learned to harness as part of the quantum computing revolution.
Luis emphasizes that generative AI and large language models are already rapidly reshaping how we program computers and interact with them, and that's going to influence the future too.
The funny thing would say, let's reflect on how much is happening right now. And it's all the confluence of all the progress in HPC, in computing systems, in AI, in algorithms and everything. And just really think about that the future of what we can do with computing is just amazing. And I don't think we are likely to live a moment like we're living right now in a long time.
To learn more about our guests and for additional resources and reading on neuromorphic, quantum, and molecular computing, please check out our show notes at scienceinparallel.org. This concludes Season 3 of Science in Parallel. Thank you for listening, and please subscribe on your favorite platform. We'd love to hear your feedback and suggestions. There are links to reach us by email and Twitter in our show notes. Science in Parallel is produced by the Carl Institute and is a media project of the Department of Energy Computational Science Graduate Fellowship Program. Any opinions expressed are those of the speaker and not those of their employers, the Carl Institute, or the U.S. Department of Energy. Our music is by Steve O'Reilly. This episode was written and produced by Sarah Webb and edited by Tess Hansen.